Welcome to lecture number 12. Today we are going to look at stereoisomerism. Stereoisomerism is another type of isomer in chemistry. We looked at constitutional isomers in a previous chapter. Constitutional isomers have the same structure, the same formula, but a different structure. So we looked at ethanol versus dimethyl ether, I believe was the example we had, where we had two molecules that are clearly different. They have different structure, but they have the same formula. The stereoisomers that we're going to look at today are a little bit different. They have the same formula, as do all isomers. They have the same structure, but they have a different three-dimensional arrangement. And this is typically going to be around carbon. In this course, it will essentially only be around carbon. Although it is possible to have stereoisomers around other atoms as well, we will really just be focused on carbon. So what do I mean by this? So I just drew some generic carbon chain here, and I drew the letter C out for one of these carbons, and let's take a closer look at it. I'm going to give this carbon R1, which just stands for some generic group R, and R2, a different generic group. This carbon here, I just drew an arrow to. That carbon has four unique groups attached to it. We have a 3-carbon chain, we have a 2-carbon chain, and then we have this general group R1 and this other different general group R2. This carbon has 4 unique groups attached to it. And when we consider stereoisomerism, we talk about the arrangement of those 4 bonds around that carbon atom. We also have stereoisomerism with regard to double bonds. This would be considered a cis double bond, a di-substituted double bond where the 2 groups are on the same face. Or we could have a trans double bond. You've probably heard of trans fats before. Trans double bonds are di-substituted double bonds that have groups on different sides or different faces of that double bond. Today, we will really be mostly focused on this type of stereoisomer, looking at a chiral carbon with 4 different groups attached to it and figuring out what types of stereoisomers we could draw. So let's begin our discussion on stereoisomerism by defining this word chirality. This is a word that we will hear a lot. So chirality, just in general terms, refers to objects that are not superimposable on their mirror images. Okay, if you have 2 objects that are not superimposable on each other, they're chiral. Okay, so look at your hands, for example. Your hands are chiral objects because they are not superimposable on each other, but they are mirror images of one another. So your left hand and your right hand are mirror images, but they are not exactly the same, right? You can't place your left hand on top of your right hand and everything would line up perfectly, right? They're mirror images, but not superimposable. So your hands are chiral. So when do we have chirality in organic chemistry? We have chirality whenever we have a carbon atom bearing 4 unique groups. If you have a carbon atom with 4 unique groups, you have what we would call a chiral carbon. There's a lot of other names for it. Could be a chiral center, stereogenic center, stereocenter, or you could replace the word center with carbon. So there's a lot of different ways to name this. But at the end of the day, if you have a carbon that has 4 unique groups, then you have a chiral carbon. And if you have a chiral carbon in a molecule, then you have a chiral molecule. Okay, we'll get some practice with this. Let me take an example here, 2-butanol. 2-butanol. How would this look? Well, butane is a 4-carbon chain. 2-butanol means there's an alcohol in the 2nd carbon. So there's 2-butanol. Now, the first question is, which carbon is a stereocenter, or which carbon is a chiral center on this molecule? We have 4 carbons, 1, 2, 3, and 4. A stereocenter, or a chiral center, a chiral carbon, has 4 unique groups attached to it, and that would be carbon 2. Carbon 2 has 4 different things attached to it, so therefore carbon 2 is chiral. So if we have a chiral carbon on this molecule, that means that this molecule, 2-butanol, is chiral. Okay, hopefully you're with me so far. Now, what I'm going to do is I'm going to draw 2-butanol. I'm going to draw one stereoisomer of it. And now we're going to draw the mirror image of it. Okay, we're going to draw the mirror image of it. I'm going to draw a dotted line here, which will represent the mirror that I'm drawing, the reflection. So let's draw the reflection of this molecule, the mirror image. And we get this structure here. Okay, see, hopefully you can see how I drew the reflection of this molecule across this dotted line to get the mirror image. Okay. So on the left, I'm going to call this 1. On the right, I'm going to call this 2. So 1 and 2 are mirror images of one another. Now the question is, are they superimposable? So now is when we're really going to start considering the 3-dimensionality of molecules, flipping them around, moving them around. And so if you're not very comfortable visualizing this, then a molecular model kit is going to be really helpful for you. You can build the structure of 1, and then you can build the structure of 2, okay? If you don't follow along with me here. So what I'm going to do to check and see if these are superimposable on one another is I am going to take molecule 2. I'm going to envision scooping it up with a spatula and flipping it over like a burger or a pancake. And if I flip this molecule over, then I end up with this. Now, if that didn't make sense to you, I would recommend building a model, but I'm going to walk through it a little more slowly. This oxygen on molecule 2 is coming out towards us and upwards. If we were to take molecule 2 and flip it over, draw it from the other side, this oxygen that's coming out towards us will be going away from us if we flip it. That's why we're drawing this from a wedge to a hash, because we're also changing the carbon skeleton underneath it. Okay? So these 2 molecules on the right, these are the same molecule, it's just flipped. So let's compare 1 and 2. After we flip it there, we have molecule 1 where the OH is a wedge, and then we have this molecule 2 where the OH is a hash. So we've drawn the mirror image of 2-butanol right here, and then we've simply flipped it so that the carbon skeletons look the same. And you can see after our little transformation, all that happened is we took the wedge and we changed it to a hash. Okay? So if that didn't quite make sense, I would rewatch that section again. Okay, we started with 1. We started with this stereoisomer of 2-butanol. We drew the mirror image of it, and then we flipped the mirror image over like a pancake. So comparing 1 with its mirror image, 2, we can see that by drawing the mirror image, we simply change the wedge to a hash. Okay? So these 2 molecules relative to each other are called enantiomers. These are called enantiomers. Enantiomers are a pair of molecules that are mirror images that are not superimposable. Okay. And again, not superimposable means exactly the same. So I'm going to write a definition here. A pair of molecules that are mirror images but not superimposable. So we've drawn here a pair of enantiomers. We started with this 2-butanol, where the OH is a wedge. We drew the mirror image. So therefore, these two molecules are enantiomers. They're mirror images of one another, but they are not superimposable. If they were superimposable, it means that we did not have a chiral molecule to begin with. A chiral molecule containing a chiral carbon, by definition, has a unique mirror image. Okay. This can all get a little bit confusing, but I will make sure to break it down a little bit more as we go. And once we see some examples, it should make much more sense. So let's look at another example. Let's take this molecule here. We have 2-chlorobutane. Again, a 4-carbon chain with chlorine on the second carbon, just like the previous example we saw. So how would we draw the enantiomer for this molecule? Well, we can do it in one of two ways. How to draw an enantiomer? One of two ways. So we can draw the mirror image. And you can draw this mirror image from any perspective. You could draw a mirror underneath the molecule. You could draw a mirror to the right, to the left, above, below. You could put the mirror anywhere. Anytime or any direction you draw the mirror image from is perfectly fine. The other way you can do it is simply change all the wedges to hashes and all the hashes to wedges. It is important, however, to keep the rest of the molecule the same. This is very important. If you're going to simply change wedges to hashes and hashes to wedges, you need to keep the rest of the molecule exactly as it is. Okay? So 2 is much more easy. If we go with method number 2, I think it's very simple to draw an enantiomer. All you do is you simply keep the rest of the molecule the same, and then you change wedges to hashes and hashes to wedges. So I think that's the easiest way to draw the mirror image, but we could also go with number 1. Method number 1 is probably more reliable, and I think it's good practice as well. So let's draw a mirror, a plane here, and let's draw a reflection. Draw a reflection of the molecule like this, and then put the chlorine. So this is a perfectly acceptable answer as well. This would be the enantiomer here of 1. Now you'll notice it's a wedge in both cases. That's because we're looking at the backside of molecule 2 here on the right. If we want to line these up so they look the same, we can flip it over. We can flip this molecule over, and then it would look like this. Again, if you're not understanding the flips of the molecule or the 3-dimensionality, the wedges and the hashes, molecular model kit. will definitely save you. Okay. So let's draw another example here. The more examples you will see, the better. What about this molecule? What would be the enantiomer of this molecule? Keep everything exactly the same and change the wedge to a hash. Alternately, you can draw the mirror image. Let's draw it from a different spot. Let's draw it down here. I will draw the reflection of this molecule. Okay. So 1 is our starting molecule. Here's the enantiomer of it, 2, and here's 2 drawn differently, but it's the same molecule. So 2 up here and 2 down here are exactly the same. I got 2 up here in the box simply by changing out the wedge for a hash. And I got down here the 2 in a circle I got by drawing the mirror image. So hopefully you can see that 2 is the same as 2 in the box and the circle. These are exactly the same, just drawn differently. Let's translate. Let's take this circular, the number 2 in the circle, and let's first rotate the molecule so the bromine is up top. So I'm going to, let's draw it over here. I'll start right over here. I'll redraw this. The first thing I'm going to do is simply rotate the molecule so that bromine is on top. If we did that, bromine would be up here, and the double bond would be over here. Now, in order to go from here to the next part, I'm just going to flip the molecule over. I'm going to envision putting a spatula under this molecule, flipping it over. And if we did that, that double bond would end up on the other side. And the bromine that's coming out towards us will now be going away from us. So now you can very clearly see that these two molecules are exactly the same. I just got them via different routes. So again, the more straightforward and simple route is to simply exchange the wedge for a hash. But if you want to draw the mirror image, that's perfectly fine as well. You can draw the mirror image from any axis. As long as you draw it properly, you'll get the right answer. Okay. So I'm assuming that most of you will not be drawing mirror images and simply switching the wedges for hashes, which is perfectly fine. That's obviously my preferred method as well. So if we had a molecule like this, OH, and we want to draw the enantiomer, we simply draw this. Okay, nice and easy. This would be a pair of enantiomers. These are mirror images of each other, non-superimposable. Okay. What about this molecule? Let's take a second to think about this. Is there an enantiomer for this molecule? Well, we can draw the mirror image of it. Let's draw the mirror image, and we'll see if it's non-superimposable or not. Well, there's the mirror image, and it's exactly the same. We literally drew the same molecule. Therefore, those mirror images are superimposable. So this actually is not a chiral molecule. We would call this achiral. Why is this molecule achiral? Well, we drew a wedge here, but it really doesn't matter if we draw a wedge there. Why? Because this carbon that I put a star next to is actually not chiral. This is an achiral carbon. This carbon is not connected to 4 unique groups. We do have a hydrogen, we have a bromine, but we have the exact same carbon chain going down to the left and down to the right. Those are exactly the same. Okay. Another example of this would be something like this. If we had isopropanol, isopropanol is not a chiral molecule because if we draw a wedge or a hash, doesn't matter, I'm just going to draw it as a wedge. This central carbon is not chiral because it's connected to 2 methyl groups. Remember, for a chiral center, we need 4 unique groups on that carbon. Okay? So anytime you have an empty ring system, it could be a 5-membered ring, 6-membered ring, anytime you have something like that, it doesn't matter if you draw a wedge or a hash because this is an achiral molecule. If you were to simply take this molecule I just drew and flip it over, you'd end up with the wedge. So there's no important distinction that can be made between the wedge and the hash for achiral molecules. So when we have achiral molecules like this, we simply draw a straight line like this because it doesn't matter if you draw a wedge or a hash. It means exactly the same thing. So what if we have multiple stereocenters? This is a molecule that I drew here with 3 stereocenters. We have 3 carbons that are connected to 4 unique groups. If we have multiple stereocenters and we're asked to draw the enantiomer, we just have to remember to switch every single stereocenter. So let's draw the enantiomer here. We keep the structure the same, and then we simply exchange wedges for hashes, and vice versa. Here we just have wedges. Okay, so there is the enantiomer. Okay, let's label that. There is the enantiomer of 1. Now, what if we only changed a few stereocenters? What if we did this? What if we left oxygen the same, changed this one to a hash, and then left chlorine the same? This would be what's called a diastereomer. A diastereomer. And this is another type of stereoisomer. We have enantiomers and we have diastereomers. Diastereomers, these are stereoisomers. They are not superimposable, and they are not mirror images. They are not superimposable, and they are not mirror images. Okay, so hopefully you can see by now that 1 and its enantiomer are mirror images of one another. 1 is a reflection of 2, right? 1 and 2 are reflections of each other. If some of the stereocenters change, but others don't, that means they're no longer mirror images. So this molecule down here, molecule 3, is not a mirror image, but it's still a stereoisomer because we have different stereocenters throughout this molecule. So it's still a stereoisomer, but it's not a mirror image and it's not superimposable. Now there's a lot of different diastereomers we could draw. Let's draw another one. Let's change the oxygen. Let's change the methyl. And let's leave the chlorine the same. There's another diastereomer we could draw. To draw a diastereomer, all you do is you change a fraction of the stereocenters. Let's draw that up here. Change a fraction of the stereocenters from wedge to hash or hash to wedge, but not all of them. If we change all of them, then we've simply drawn the enantiomer. So to draw a diastereomer, you simply change a fraction of the stereocenters from wedge to hash or hash to wedge. Whoops, I spelled wedge. From wedge to hash or hash to wedge. Okay, so in order for this to work, you need more than one stereocenter for a diastereomer. You need more than one stereocenter for a diastereomer. Okay, if you have a molecule with only one stereocenter, there are no diastereomers. In order to find the total number of stereoisomers you have, the total number of stereoisomers is equal to this equation, 2 raised to the n, where n is equal to the number of stereocenters. N is the number of stereocenters. So if we had a molecule that has 3 stereocenters, like the one above here that I drew, this would be 2 raised to the 3, or 8 possible stereoisomers that we could draw. We can draw a pair of enantiomers, right? We can draw a pair of enantiomers, and then we can draw 6 diastereomers. 6 different diastereomers for a total of 8 stereoisomers. Okay? We drew a couple of them here where we changed a few different groups. And in order to get the others, you would simply change around the other groups. We're looking for all the different possible combinations of wedges and hashes. Okay. Okay, so that's where I think we'll stop this lecture. This was a lot of new information, and to a lot of people, this is pretty difficult to initially grasp, which is completely understandable. If it didn't make sense, rewatch it again. And I definitely recommend building some of these, or even using some computer software if you have access to some chemistry programs. Really helpful in understanding how these molecules exist in 3D. We're going to get a lot more practice with this next lecture, as well as the workshop. So even if it doesn't make a lot of sense right now, just hang in there for now. Okay, see you in lecture 13.